Authorization code grants with proof key for code exchange. So in this short walkthrough, I'm going to be showing you what the hell all those big words mean. The flow is quite complex, but hopefully we can break it down and make things a little bit simple. So in this flow, we have four actors: the user, app, identity provider, and the backend service. The user, or in OAuth 2 speak, the resource owner, this is the person who owns the resources, such as a person with a bank account. Then we have the app or client in OAuth 2 speak, and the app is like, say, a mobile banking app on your smartphone or your Facebook or Twitter app. Then you have the authorization server. So this is the machine which stores all of your credentials. And finally, the service, which is the resource service, so the machine holding all of your data, like a bank account or Twitter, who holds all your tweets, etc. There are generally two kinds of clients or apps, and these might be confidential or public clients. Confidential clients, they've got the ability to store secrets or passwords securely. So in an environment file or a local database, they might be like a PHP app or Java or Node or Go app. So usually like machines or back-end servers. Then there are public clients. So these might be native or mobile apps and single-page applications. Public clients, they're not able to store your client secrets securely because they're just that public. In a single-page application, you could right-click, inspect element. In a native app, you could download and somehow access the source code by, if you're able to gain access to that app on your mobile device. So, in order to combat this, the implicit grant was created with a redirect flow, and this would allow you, with the ID of the app, so the client ID, the implicit flow would redirect you to the authorization server. You would log in, and then assuming the happy path, the authorization would redirect back to the callback URL that was specified in the initial request. But instead of the authorization code, you'd actually get an access token, and this access token would then be used to access those resources. This makes the implicit grant very simple but also quite insecure, because the query string is easily readable in that redirect, because the access token would be returned in a query string. The authorization server has no guarantees at all that the app ever received that access token. So in order to combat this, the authorization code grant is recommended. It's not recommended to use the implicit grant anymore. And so in this flow, rather than the authorization server returning the access token, what it actually does is returns back to the callback URL with an authorization code. Now, this authorization code is like a one-time usage passcode returned to the client, and the client would then exchange that code, that authorization code, for a token in the authorization server. So return back the authorization code, and then the client can send a post request, which is a lot more secure than sending in a query string directly to the authorization server, which means that the authorization server has guaranteed that the authorization code has been received by that client. And then in that authorization code flow, the server would then return the access token back to the client. So this is much more secure than the implicit grant, but even then it's susceptible to the authorization code, what's known as the authorization code interception attack. So a malicious app installed in the browser could intercept that authorization code, and then the attacker could then snatch that code and exchange that for an access token. The attacker's got access to your bank account. So as an extension to this OAuth 2 authorization code flow, this problem was kind of solved or mitigated with PKCE. So this is known as proof key for code exchange. The way that it's solved is that the client initially generates a code verifier, which is like a random string or random passcode or something like that. And then what it would do is hash that, for example, SHA-256 checksum, and creates a code challenge. But it keeps that code verifier locally in memory or session storage or something like that. So when it redirects to the identity provider and then goes through this whole flow, eventually we come back down here and redirect to the callback URL with the authorization code. But then what it will do is send what the app will do is send the original code verifier before it was hashed to the identity provider. Now the identity provider can then perform the hash on that code verifier to ensure that it matches the code challenge that it initially received. And by doing this, what the authorization server has done is ensured that the client has had proof of possession. So the idea is that an attacker, if they had even attained that authorization code, well, the chances are that they haven't also got that initial code verifier in the beginning. So it's that simple. Thanks very much.